Today we're doing problems relating to section 9.2, the two-sample t-test. And I'm not assigning a homework on these problems. So that being said, these example problems, and there is one problem on the review as well, but these are highly relevant to the exam for Thursday. So please spend some time looking through these again after class today. Let's look at the first problem here, which looks at an experiment that compared the air permeability of two types of fabric, cotton and triacetate. Samples of size 10 were collected from each kind, and we have both for the cotton and triacetate samples, the mean and the standard deviation of air permeability. We also assume that the normal distribution holds here for air permeability in both types of fabric. And so the goal is to determine whether there is a difference on average between the two types of fabric. If you read that last sentence, it just says the goal is to determine whether there is a difference or not between the two. So it's not specifying a size of the difference. It's not giving you any directional information. That just means when you set up your null and alternate hypotheses, if we define delta to be the difference, the mean air permeability of cotton minus the mean air permeability of triacetate, then our null hypothesis is that the mean difference is 0, and the alternative is that the mean difference is different from 0. Now, next, we want to calculate the value of the test statistic. So we need to know what our observed difference is. So I'm just going to stick with the C and T notation here. So C bar for the average air permeability of cotton, etc. And in this case, that means it's 51.71 minus 136.14. So at least based on what we observed, there is a pretty substantial difference between the two. But the observed difference on its own is not informative. We have to convert it to a test statistic to make that ultimate determination. So our test statistic is the observed difference minus the hypothesized difference. And then in this case, it's each sample variance over each sample size square root. So just in case anyone has questions at this point about why I'm using the T statistic, it has to do with the fact that the normal distribution is assumed, so we have normality, but we do not know the underlying population variances. If the population variances were known, you could use a z-test. But since we only have the sample variances available, that means we have to make an adjustment. And because we're using sample variances, we have to use a t-distribution as reference. So let's plug in all these relevant quantities. And if you go and do a little bit of simplification here, you will get a test statistic of negative 72.642. Now, at this point, we don't yet know what reference t-distribution we're using. We need to figure out what the degrees of freedom are. But if you've developed any intuition around this, you should be looking at that t statistic and recognizing it is going to have a very, very small p-value regardless of what the degrees of freedom are. So since we're, if you look ahead to part E, we're doing this test at the 5% level of significance, intuition should already suggest you're probably going to reject the null hypothesis. But let's go through the steps for determining that. Part C is asking us to calculate the degrees of freedom for the test. Now, in this problem setup, you're not given any information beyond it being stated what the sample variances are. If there's any information telling you that you can assume equal variances, it will simplify the problem. And that we'll look at in our next example. But here, we do not have that, so we cannot assume equal variances, which means we have that pretty monstrous formula for degrees of freedom. Now, I am going to just do a shortcut way of writing that out here. You can convert the formula. It doesn't save a whole lot of time, but if I define the following two quantities, for my first sample, I define SE, and that's shorthand for standard error. So for the cotton sample, that's the standard deviation divided by the square root of the sample size, which in this case is 0.2498. And I can do the same thing for the triacetate sample, which in this case ends up being 1.1353. So now this formula is still unwieldy, but writing things in terms of these SE quantities does save a little bit of writing. So it's the two SE quantities squared, sum of those squared, over the SE quantities to the power 4, each over sample size minus n minus 1. So m minus 1 and n minus 1 respectively. You can just directly plug quantities into the full formula. You don't have to make this SE substitution. They're numerically equivalent. This just ends up being a little bit faster computationally. So we can now do substitution, and I trust all of you can do this. I'm not going to spend 5 minutes just plugging numbers into a formula and doing the calculation. What you should eventually get to here is roughly 9.87, and the rule is always you round down degrees of freedom, or you take the floor. So in this case, we will use 9 degrees of freedom for our test statistic to calculate the p-value. Which is the next thing we are asked for here, calculate the p-value. Now, our alternative here is two-sided. So two-sided alternative means p-value is 2 times, in this case, the TCDF evaluated at the negative of the absolute value of the test statistic and 9 degrees of freedom. And if you go and evaluate this, you're going to get 0, to probably 6 or 7 decimal places. So our p-value is effectively 0 here. So what is our conclusion? Well, our p-value of 0 is definitely below the 5% threshold of alpha. So we are going to reject the null hypothesis. Importantly, you have to write a conclusion in terms of the problem statement. So you are going to say something to the effect of, the sample evidence suggests that average air permeability is not the same for the two types of fabric. Okay, because it's two-sided, we didn't set up our test in such a way that we can definitively say which one has better average air permeability. But we can always look at that doing something like a confidence interval. So last part of the problem here is in fact asking you to construct a confidence interval for delta, the difference between the average average air permeabilities of the two types of fabric. Now, the confidence interval we're looking for here is one at the 95% level, which means we need to go and find a critical t-value with area to the right 0.025 and 9 degrees of freedom. So on your calculator, you would use the t inverse function. Area would be 0.975, degrees of freedom would be 9, and this will give you a t-value of 2.262. So now your confidence interval is given by delta hat plus or minus that t-value times the square root of the weighted variances summed. And this ends up being negative 84.44 plus or minus 2.262 times square root of 1.3512. So your confidence interval ranges from negative 87.069 to negative 81.811. So that gives you a range of plausible values that with 90% confidence represent the true difference between average air permeabilities of the fabric. And since this whole range is negative, remember we're looking at cotton minus triacetate. So we're saying cotton minus triacetate is likely negative. So what we're saying is that cotton has a lower average air permeability than triacetate. Sorry, let me just fix this here. So that's what you can conclude from the confidence interval. You're able to make a bit more of a definitive statement by interpreting that than just rejecting the null hypothesis in this instance. Now, this is the kind of horrific version of the problem, only because of the degrees of freedom calculation. That's a rather tedious thing to do. So let's look at the kind of more friendly way in which a problem like this could show up. So we're looking at problem 9.4. Here we're comparing two braking systems, and the specific metric is we're looking at the average stopping distance for each system if the brake system is engaged at a speed of 50 miles per hour. We are again assuming that the stopping distance follows a normal distribution for both systems. We are also assuming that the normal distributions have common variance. That's the key phrase that you're looking for that really provides some simplification for the problem. And then we'll get to the sample statistics in a moment. 6 observations under one system, 8 observations under the other, and we have those average stopping distances and standard deviations. And in this case, our null hypothesis is actually anticipating a specific difference. It's saying under the null hypothesis, again, if I define delta, in this case to be mu x minus mu y, our null hypothesis says on average, the difference is 10 units. Like braking system number 1 minus braking system number 2, we expect to be 10. Like that, there's an equivalent way of writing our null hypothesis that the braking system X on average stops 10, what are the units here? 10 meters sooner than braking system number Y. And our alternative says that the difference is less than negative 10. So again, interpretation-wise, that less than negative 10 means even sooner, right? It'll be a number below negative 10, so a larger difference in this case. Part A is asking for the pooled estimate of variance, and that is something you can only calculate again when you have an assumption of common variances. So the pooled estimate of variance formula for each sample, it's the sample size minus 1 times the sample variance. You sum those quantities, and then it's the sum of the sample sizes minus 2. So in this case, it'll be 5 times 5.03 squared plus 7 times 5.38 squared, all of that divided by 12. And so our pooled estimate of variance is 27.426. Now we want to calculate the value of our test statistic. So again, we need to know what the observed difference is, which in this case, we just take the difference of the two sample means, and we observe a difference of negative 13.6. So we do observe something that's, saying X seems to be stopping a little bit sooner than 10 meters. Like on average, we actually saw 13.6 meters. But we can formalize this by calculating a test statistic, delta hat minus delta naught. And then because you have a pooled estimate of variance, you then divide by the square root of the pooled estimate of variance times 1 over first sample size plus 1 over second sample size. And this ends up being negative 1.273. So if we're going to evaluate the p-value, we need the degrees of freedom. If you have common variances assumed, it's the sum of the sample sizes minus 2. Like, so much easier than what we did in 9.3. So in this case, 12 degrees of freedom. So we can calculate our p-value. Now, very importantly here, our alternative in this case is directional. It's one-sided. So that needs to be reflected in our p-value. Our p-value in this case is just going to be what the area is to the left of or below our test statistic, with 12 degrees of freedom, which in this case ends up being 0.114. So even though we observed a difference that was a little bit larger than negative 10, our p-value ends up being large. Like at the 5% level, our p-value is larger than 0.05, which means in this case, we do not reject the null hypothesis. What does that tell us? The sample evidence does not show a difference on average of more than 10 meters. Now, is it possible that brake system X is actually superior, I mean, more superior in that it stops faster or sooner than 10 meters? Yes, but our sample size may not be large enough to actually reflect this. Remember, all of this is also sample size dependent. So if we went and increased our sample size, which in this case is pretty small, 6 observations in one case, 8 in the other, we could come up with a more definitive statement if our sample size were larger. But what does the sample evidence tell us? We can construct a confidence interval. So we again want 95% interval, which means we need t-value, area to the right, 0.025, 12 degrees of freedom. So you'll use t inverse with area 0.975, 12 degrees of freedom, and that gives you, in this case, 2.179. And now when you calculate your confidence interval, you use this pooled estimate of variance to do that, which in this case if I do that specific calculation, let me write it this way. We get a confidence interval of negative 19.763 to negative 7.437. So at least in terms of superiority, we can say braking system X seems to be superior, right? Because plausibly, it's very nearly 20 meters sooner is one side of the confidence interval. Worst case scenario suggested by our confidence interval is that it only stops about 7 meters sooner. So the null hypothesis value of negative 10, that's inside the confidence interval. So confidence interval is consistent with the conclusion from our hypothesis test. But if it's just about superiority of the system, yes, braking system X should be used because it does seem to have much better performance than system Y, even worst case scenario. I have one more example here for us to look at.
I have a question.
Yeah, sure.
Part A, when we're stating the conclusion,
Yes.
Would we not be able to state something like the sample evidence suggests that on average the difference is negative 10?
Yeah, you could phrase it that way too. That would be equally acceptable to what I wrote down here.
Okay, cool. Just want to make sure.
Yeah.
Thank you.
Okay, so 9.5 should look very similar to 9.4. The main thing is that it doesn't have like listed out steps asking you to do particular things. It just gives a problem setup and asks you to reach a conclusion at a certain level of significance. So in this case, you know, problem just says you have samples from two normally distributed populations. So we have assumed normality. We have our sample statistics. We are also assuming that the underlying populations have equal variances. That's a nice assumption to have because it allows us to do the pooling, things simplify a little bit. And when we're fishing out what our hypothesis is, it says it's of interest to test whether the X population has a mean that is 5 units larger than the Y population, or whether the difference is not equal to 5 units. We want to do this test and state a conclusion at the 10% level of significance. So our null hypothesis, again, if I go and define delta as the difference between the two means, we are trying to determine whether X has a mean that is 5 units larger than the mean of Y. So if we look at the difference, we want that to be 5. So our null hypothesis is that the difference is 5. Our alternative says the difference is not equal to 5. There's no directional information here. It's just a generic two-sided alternative. Next thing we want to do is calculate our test statistic, but we need two things to do that. Firstly, we need to know what the observed difference is. Which in this case is 7.3 units. And we also need our pooled estimate of variance. And pooled estimate of variance in this case is 20.43. So now we can calculate our test statistic. Let's just plug in all our values here. And this works out to be 1.49. And we want to evaluate that using a t-distribution with 33 degrees of freedom. So we can go and calculate our p-value. It's two-sided, so that is reflected in how we calculate our p-value here. Remember, you always use the negative of the absolute value of the test statistic. And 33 degrees of freedom in this case. So this works out to be 0.146. So in this case, again, our p-value of 0.146, it's greater than 0.1, which is our alpha in this case. So we do not reject the null hypothesis. Now, just the way this problem is set up, it's a little bit more difficult doing an exact interpretation because there's not a lot of context given here. You're just being told, you know, you have two populations, et cetera, et cetera. You're not being told what it is that you're measuring. Even so, you still want to go and write down sample evidence suggests, or sample evidence is consistent with the true difference being 5 units. There's no evidence to suggest that the true difference is anything, is not 5 units, right? You could go and construct a confidence interval here. I didn't ask for that in this particular instance, but I think everyone should feel pretty confident doing that calculation as well.